Hello, welcome students. I am Rekha Thorat, Associate Professor. Today we will consider some theorems. Let statement of this theorem is let H be a subgroup and K be a normal subgroup of the group G. Then H intersection K is normal in H. That means we have to prove that H intersection K is normal subgroup in H, where H is subgroup and K is normal subgroup of the group G. Let us consider the proof of this theorem. Here we assume that let G be a group and let H be a subgroup of group G and K be a normal subgroup of this group G. Since here H and K are subgroups of group G and H intersection K is subset of H. We know that H intersection K is subset of H. Therefore, H intersection K is subgroup of H. Since H and K are subgroups of group G, H intersection K is subgroup of H. Now we have to prove that this H intersection K is a normal subgroup of H. Let G belongs to H and H belongs to H intersection K. Since H is a subgroup of group G, therefore G belongs to H and H belongs to H implies, we know that definition of subgroup, since H is a subgroup of group G, therefore G belongs to H and H belongs to H, and this implies G inverse belongs to H. Also G belongs to H and this implies G belongs to G and H belongs to K. But we have given that K is normal in G. Since K is normal in G, therefore by definition G inverse belongs to K. That means if K is normal in group G and K is a subgroup, then G inverse belongs to K. We have seen that theorem. Thus, we have seen that G inverse belongs to H. Also G inverse belongs to K. So that G inverse belongs to H intersection K for all G belongs to H and for all H belongs to H intersection K. That means here in the statement of the theorem we are given that H is a subgroup and K be a normal subgroup of the group G. And here we have to prove that H intersection K is normal in H. In the proof we have assumed that G be a group and H be a subgroup of group G and K is normal subgroup of group G. Here, since H and K are subgroup of group G, H intersection K is subset of H. Therefore, H intersection K is subgroup of H. Now we have to here prove that H intersection K is normal subgroup of H. To prove this, we have assumed that let G belongs to H and H belongs to H intersection K. Since H is a subgroup of group G and therefore G belongs to H and H belongs to H, and this implies GHG inverse belongs to H since H is subgroup of group G. Also, here G belongs to H implies G belongs to G since H is subgroup, and H belongs to K. Since K is normal in group G, we have given in this statement K is normal in G. Therefore, by definition of normal subgroup, GHG inverse belongs to K. Thus, we have proved that GHG inverse belongs to H, GHG inverse belongs to K. So that GHG inverse belongs to H intersection K for all G belongs to H and for all H belongs to K. That is, H belongs to H intersection K. Hence, H intersection K is a normal subgroup of H. Now we consider next concept, that is center of a group. First we consider the definition of center of group. Let G be a group and let ZG equal to the set X belongs to G such that XG equal to GX for all G belongs to G. Bracket complete. Then ZG is called the center of group G. That means center of a group G is defined as let G be a group and set ZG such that set of all X belongs to G satisfying the property XG equal to GX for all G belongs to G. Then ZG is called as center of group G. Thus, center of group G means the set ZG such that set of all X belongs to G satisfying XG equal to GX. Now we consider another theorem. Statement of this theorem is the center ZG of a group G is normal subgroup of G. Sometimes this can be asked for objective. The center ZG of a group G is dash dash. It is normal subgroup of G. Or ZG equal to set of all X belongs to G such that dash dash XG equal to ZG equal to set of all X belongs to G such that dash dash, that is XG equal to GX. For objective, such type of questions can be asked. Or this can be asked as let ZG equal to set of all X belongs to G such that XG equal to GX for all G belongs to G. This is known as center of, this is known as dash dash center of a group. Now we consider proof of this theorem. We have to prove that center ZG of a group G is normal subgroup of G. Let us assume that G be a group and we have center of a group, that is ZG equal to set of all x belongs to G satisfying the property xg equal to gx for all G belongs to G. Here we have to prove that ZG is a normal subgroup of G. First we prove that ZG is a subgroup of group G. Let x1 comma x2 belongs to ZG. Then by definition of center of group xg equal to gx, that is for x1 belongs to ZG, x1g equal to gx1, and for x2 belongs to ZG we get x2g equal to gx2 for all G belongs to G. Thus we have x2g equal to gx2 for all G belongs to G, and this implies x2 inverse into in bracket x2g bracket complete into x2 inverse equal to x2 inverse in bracket gx2 bracket complete into x2 inverse, and this implies gx2 inverse equal to x2 inverse into G. That means gx2 inverse, since x2 inverse into x2 is identity, gx2 inverse equal to x2 and x2 inverse equal to identity x2 inverse into G for all G belongs to G. This implies x2 inverse belongs to ZG. Now in bracket x1 x2 inverse bracket complete into G equal to x1 in bracket x2 inverse into G bracket complete equal to x1 in bracket G x2 inverse bracket complete equal to in bracket x1g bracket complete into x2 inverse. And this is equal to G x1 x2 inverse equal to G x1 x2 inverse, and therefore x1 x2 inverse belongs to ZG for all x1 x2 belongs to ZG. Hence ZG is a subgroup of group G. Now we have to prove that this ZG is a normal subgroup of group G. Here first we prove that X for x1 x2 belongs to ZG, ZG is subgroup of G. To prove that ZG is subgroup of G, we consider x1 x2 belongs to ZG, so that we get x1g equal to gx1, x2g equal to gx2 for all G belongs to G. Now we consider here x2g equal to gx2. Now multiplying both sides on left and right by x2 inverse on LHS and RHS, and after simplifying x2 inverse in as x2 inverse into x2 is identity element, we get gx2 inverse equal to x2 inverse into G, since x2 into x2 inverse is identity element. Thus we get x2 inverse belongs to ZG, since gx2 inverse equal to x2 inverse into G, that is gx equal to xg property is satisfied. So that x2 inverse belongs to ZG, x2 belongs to ZG. Then we consider x1 x2 inverse into G equal to x1 x2 inverse in G by associative property, only bracket is changed, is equal to x1 x2 inverse into G is equal to G into x2 inverse, which is equal to x1G into x2 inverse. That is only associative property is used. So that we get here G x1 into x2 inverse, and which is equal to G into x2 inverse means x1 x2 inverse, that is G into x1 x2 inverse, associative property is used. Thus x1 x2 inverse belongs to ZG. Now here we have to prove that ZG is subgroup, but ZG is normal subgroup of G. To prove this, let G belongs to G and X belongs to ZG. Then GXG inverse equal to G in bracket GX bracket complete into G inverse equal to GX equal to XG in bracket into G inverse, as it is equal to G into G inverse is identity element equal to X, which belongs to ZG. Thus, G belongs to G, X belongs to ZG. This implies GXG inverse belongs to ZG, and hence ZG is a normal subgroup of group G. Thus, we have proved that center of a group is normal subgroup of G. That is, ZG is center of a group is normal subgroup of group G. Thank you.